Good day. The topic we are treating today is properties of geometric progression by Okola Monsurat Olajumoke. This lesson is a continuation of the topic geometric progression and its properties. Before the commencement of this lesson, you must have been familiar with the topic arithmetic progression and geometric progression. In this lesson, some properties of a geometric progression are established and proved. By the end of this lesson, I hope you will be able to apply its properties where necessary. Properties of geometric progression. The first property. When each term of a geometric progression is multiplied or divided by a same non-zero quantity, the new series forms a geometric progression having the same common ratio. Proof. This proof is divided into two parts. The first part is multiplying the terms of a geometric progression by a non-zero constant quantity, and the second part is dividing the terms of a geometric progression by a non-zero quantity. Now, let a, ar square up to arn and so on, tagged as equation 1, be the general form of an arithmetic progression with first term a and common ratio. To generate the common ratio is either you divide the second term by the first, which is equal to dividing the third term by the second, which is equal to dividing the n plus 1 term by the nth term, which we all give r as the common ratio for all n elements of natural number. So now we move to the first part of the proof, that is multiplying by a non-zero quantity. Let k be a non-zero quantity, a non-zero constant, that is, it is not equal to 0 and it is a constant. So multiplying each term of 1 by k, we obtain the sequence ka, kar squared, kar cubed, up to kar raised to the power n, and so on. And that is tagged as the second equation. Clearly, if you want to get the common ratio of this new sequence formed by multiplying a constant quantity k with the terms of a geometric progression, so to check if this also forms a geometric progression, we have to check if it has a unique common ratio. That is, if you divide the second term by the first, you must get the same result as dividing the third term by the second, which must also be equal to dividing the n plus 1 term by the nth term. So clearly we know that kar over ka will give r, kar squared divided by kar will also give r, up to kar raised to the power n divided by kar raised to the power n minus 1 will give n. Since it has a unique common ratio, therefore the new sequence 2 also forms a geometric progression with common ratio r. For example, if you have 6, 18, 54, 162 and so on, this is a geometric progression with its common ratio as 3. If we multiply each terms of the above sequence by 3, that is, if you have a new sequence 18, 54, 162, 486, the common ratio will also be 3. And that is what the first property is talking about. If you multiply each term of a geometric progression by a constant non-zero quantity, we also have a geometric progression with the same common ratio. So here, we move to the second part of the proof, division by a non-zero quantity. Let k be a non-zero constant, so dividing each term of a geometric progression by the non-zero constant k, we obtain the sequence a over k, ar over k, ar squared over k, ar cubed over k, up to the n plus 1 term ar raised to the power n over k. And this is the new sequence formed by dividing each term of 1 by k. So to check if this is an arithmetic progression, we know that a over k is the first term. So to check if this is an arithmetic progression, we have to divide the second term by the first, the third by the second, the fourth by the third, which must all be equal to dividing the n plus 1 term by the nth term. So this is it here, and if we should evaluate this, we all get r. Since it has a unique common ratio, therefore the new sequence obtained by dividing each term of a geometric progression by a non-zero constant k also forms a geometric progression. Therefore, when each term of a geometric progression is multiplied or divided by its same non-zero quantity, the new series forms a geometric progression having the same common ratio. And that completes the proof of the first property. Now we move to property 2. In a geometric progression, the reciprocal of the terms also form a geometric progression. That is, if you have the terms of a geometric progression and you take its reciprocal, the reciprocal of that particular term also forms a geometric progression with a unique common ratio. Now we'll move to the proof of the second property. Let 1, that is the first equation, be a geometric progression with first term a and common ratio r. And we know that this is how we obtain the common ratio of a generalized geometric progression. It has a common ratio r for all n elements of n. So now we form a new sequence by dividing each term of 1 by a constant, by taking the reciprocals. We form a new sequence by taking the reciprocal of the terms of the geometric progression 1, and which is 1 over a, 1 over ar, 1 over ar squared, up to the n plus 1 term, 1 over a r raised to power n, and that gives the fourth equation. So here, this is a sequence. To check if this sequence also forms an arithmetic progression, we have to check if it has a unique common ratio. That is, if you divide the second term by the first, the result must be equal to dividing the third term by the second, which must all be equal to dividing the n plus 1 term by the nth term. So from 4 here, that is this sequence generated, we have 1 over ar divided by 1 over a, and it must be equal to 1 over ar squared divided by 1 over ar, which must be equal to 1 over ar cubed divided by 1 over ar squared, which must all be equal to 1 over ar raised to power n divided by 1 over ar raised to power n minus 1. If all this is evaluated, we get 1 over r. Since it all has a unique common ratio, therefore the new sequence formed by taking the reciprocals of the term of a geometric progression also form a geometric progression with common ratio 1 over r. Hence, the reciprocal of the terms of 1, that is of a geometric progression, also forms geometric progression with common ratio 1 over r. So now we'll move to the third property. When all the terms of a geometric progression is raised to the same power, then the new sequence also forms a geometric progression. That is, if the terms of a geometric progression has the same power, then the new sequence also forms a geometric progression, that is, it has a unique common ratio. Now we'll move to the proof of this property. Let 1 be a geometric, that is the first equation, a, ar squared, a up to a raised to power n minus 1 up to a raised to power n, be a geometric progression with first term a and common ratio r. Then this is how we obtain the common ratio of a geometric progression, which is r for all n elements of n. So let k be a non-zero real number. So raising each term of 1, that is each term of the generalized geometric progression to the power of k, it gives the first term raised to power k, the second term raised to power k, the third term raised to power k, up to the n plus 1 term raised to power k, and so on. And that is tagged as the fifth equation. We have ar raised to check if this forms a geometric progression, you have to check if it has a unique common ratio. That is, you divide the second term by the first, which is ar raised to power k over a raised to power k. The third, which must be equal to dividing the third term by the second, which is ar squared raised to power k over ar everything raised to power k, which must be equal to dividing the fourth term by the third, ar cubed raised to power k divided by ar squared raised to power k, which must all give the same result as dividing the n plus 1 term by the nth term. That is ar raised to power n everything raised to power k divided by ar raised to power n minus 1 everything raised to power k. If we should evaluate each of these, we get r raised to power k as the result. That is, they have a unique common ratio for all n elements of n. And since they have a unique common ratio, therefore the new sequence formed by raising each term of a geometric progression to the power of a non-zero constant forms a geometric progression with common ratio r raised to power k. Therefore, when all the terms of a geometric progression is raised to the same power, then the new sequence also forms a geometric progression with common ratio r raised to power k. And that completes the proof. Now, we move to the fifth property. Property 5. In a geometric progression of non-zero, non-negative terms, the logarithm of each term forms an arithmetic progression and vice versa. That is, the logarithm of each term forms an arithmetic progression and the logarithm of each term of an arithmetic progression also form a geometric progression. That is, if a comma a squared, that is the terms of a geometric progression, are non-zero, non-negative terms of a geometric progression, then log a, that is the logarithm of each of these terms, will form an arithmetic progression, and this will also form a geometric, and these logs will also form a geometric progression. So let's move to the proof. Let 1 be a geometric progression with first term a and common ratio r. So if you have to take the logarithm of the nth term, if you have to take the logarithm of the nth term, that is, this is the nth term, log a r raised to the power n minus 1, which is equals to, according to the rule of logarithm, if you have log ab, the same thing as writing log a plus log b. So here we have log a r raised to the power n minus 1, the same thing as writing log a plus log r raised to the power n minus 1. Also, according to the rule of logarithm, log b raised to the power a, the same thing as writing a log b. So here log r raised to the power n minus 1, the same thing as writing n minus 1 log r. That is why we have log a plus n minus 1 log r for all n elements of n. So let b subscript n be equals to this, and you know this is equals to this, therefore b subscript n will be equals to log a plus n minus 1 log r, where this is representing the nth term. Also, if you want to, then bn plus 1, which is representing the n plus 1 term, you know, wherever you see n in bn, you substitute it with n plus 1. So here bn plus 1, here bn plus 1 will now be log a plus n plus 1 minus 1 log r, and this will give n log r. That is why we have bn plus 1 to be equals to log a plus n log r. And you know, they said the logarithm of the terms of a geometric progression will form an arithmetic progression. And to check if a particular sequence is an arithmetic progression, you must check if it has a unique common difference. That is, this is the n plus 1 term of an arithmetic progression, and the nth term is bn. So if you subtract bn from bn plus 1, that is, you subtract the nth term from the n plus 1 term, you get a unique common ratio. That is bn plus 1 is equals to log a plus n log r minus bn, which is log a plus n minus 1 log r. So if you open the bracket, you have log a plus n log r minus log a minus n minus 1 in bracket log r. So log a, we cancel log a. We are left with n log r minus multiplied by n will be minus n log r, minus multiplied by minus plus 1 multiplied by log r will now be plus log r. Plus n log r will cancel minus n log r, so we are left with log r. If you also follow this same procedure for bn plus 2 to check if we have a unique common difference, you know, is either you subtract bn from bn plus 1 or you subtract bn plus 1 from bn plus 2. So assuming we have bn plus 2 now, bn plus 2 will give us log a plus n plus 1 log r. So bn plus 2 is log a plus n plus 1 log r. So we subtract bn plus 1 from bn plus 2. We have log a plus n plus 1 log r minus log a plus n log r. And we know we have log a plus n log r plus log r minus log a minus n log r, and we are left with log r. That is, we have a unique common difference. So clearly, bn plus 1 minus bn equals to log r, which is equals to constant for all n elements of n. Hence b1 starts from substituting n equals to 1, n equals to 0, n equals to 1, n equals to 2, up to bn, that is, b1 will represent log a from here. If you have b1 will be log a plus 1 minus 1, which is 0, 0 multiplied by log r, so b1 is log a, b2 is log a r, b3 is log a r square, up to bn, which is the nth term, which is log a r raised power n minus 1. bn plus 1 will be log a r raised power n. Is an arithmetic progression with common difference log r. So now we'll prove the other side that it's also and vice versa. So conversely, let log a, that is this term, be an arithmetic progression. So we want to check if this particular term, if this particular sequence also form a geometric progression. And to check if it also forms a geometric progression, we must check if they have a unique common ratio. So let all these be an arithmetic progression as we have here, with common difference d. Then if you want to get the common ratio of the common difference of an arithmetic progression, it will be subtracting the n minus 1 term from the nth term. That is, we have log a r raised to power n minus log a r raised to power n minus 1, which is the difference, the common differences. We know that they are terms of an arithmetic progression. We know that they have a common difference. So according to the rule of logarithm, if you have log a minus log b, the same thing as writing log a over b. So log a r raised to power n minus log a r raised to power n minus 1, the same thing as writing log a r raised to power n divided by a r raised to power n minus 1. In order to eradicate log, we introduce exponential. So if you introduce exponential here, it's going to cancel the log. We are left with a r raised to power n divided by a r raised to power n minus 1. So whatever you do to the left hand side, you also do it to the right hand side. You also introduce exponential here, and that is why we have exponential d for all n elements of n. So since this is the n plus 1 term of a geometric progression, as we all know, and this is the nth term of a geometric progression, and since we divide the nth term of a geometric progression by the n plus 1 term of a geometric progression by the nth term, and it gives a unique constant, therefore the terms of that particular arithmetic progression also forms a geometric progression with common ratio e raised to power d. Hence, a geometric progression of non-zero non-negative terms, the logarithm of each term form an arithmetic progression and vice versa. Next video will be on arithmetic and geometric means with sample questions and solution. Please subscribe to our YouTube channel, like and share our videos. Thank you.